we're going to jump through here and look at the definite integral. So we've previously just looked at the area under the curve, and we sort of introduced that was the concept behind integrals or integration. Now we're going to actually look at the definite integral, which we're going to define sort of as we go along. So previously we talked about if we were looking at the area under the curve here between A and B, we could do two different methods here. We would have this method here with rectangles because the function is increasing. This is an underestimate. And we could do and I'm going to call this underestimate here the area L for lower because it's below the function most of the rectangles. This one here is our I've just moved it. Let me just come back out. This one here is going to be our overestimate, which we're going to call area U, which is the area upper. So we're looking at lower or upper. Realistically, the lower defines the rectangles sit below the function. Upper defines them as they're going above. Now, I'm just going to define a few things here. So we saw in the last one that the estimate of the area, if we can increase the amount of rectangles, we increase the accuracy. So the more rectangles we put in, the better our estimate is. Now the width, so if I break this here, I have this length here. This is this is going to be a width of B minus A. So that's the difference between B here and A. I should use a highlighter on that, not this highlighter. So B and A gives us these values here. And then if I divide these by the number of intervals I'm going to have here. So you notice here this lower rectangle, it's got a length here of, this is my first rectangle here. So I've got 1, 2, 3, 4, etc. And I'll go through to n amounts of intervals here. So I pretty much break this up by, I work out how long this distance is, and then I divide it up by the number of intervals I want. Now, each rectangle here, so the underestimate area lower, we have the width of this function here, which is given by B minus A over N, which means we've cut this up and we work out this pretty much, we've got the width of this particular unit here will be, I'm trying to think, if this was like 2 and 4 and we're breaking it up into 100 intervals, that we would look at the width here and it would be like 4 minus 2 over 100, which would equal 2 over 100. So these would all have a width of 0.02, and that would be the width of each rectangle here. So when multiplying the areas to get these rectangles, that's the width I'd put in. Now, I'll leave that for the minute. I'm going to erase it at the end just because it doesn't... So that is this width here. So the width is these values at the bottom. Maybe we should highlight them in a colour just to sort of... So this width here is this, and I'll just go... That next width there is this width here, but they're all equal width. So you'll find that these all have exactly the same length here. Now, this next bit here, I've got this F with an input value of x of 0. So that means that my first value here, x0, I put it into my function, I get the length of this side here. Now, you might be thinking, why use x of 0? And the point is that we want to go up to xn. Now, when we're doing we do these rectangles, you'll notice here in the calculation of the rectangles here, we don't actually use the xn one. This coordinate here, which would be, let me just get rid of that. This value here of fxn, we don't use in this one because it's the underestimate. We use x0, f of x0 here for our first one, all the way up to this value here, which is f of x n minus 1, which means the interval before that. Okay, so that gives us this term here. So we have the width times each y coordinate. So this is the height here, these values here. Okay, now let me just clean this up so our notes don't look quite so messy. Okay, and this can be written in a sum notation, and if we weren't using the program Interior, which if we weren't using this program on our graphics calculator, we would actually have to use sum notation like this to calculate these intervals. Okay, cool. So now we're going to go the upper estimate. Now this one here, you'll notice our first term, we actually start at x1. So in this first one, we actually ignore this. I'm just drawing this blue line here. Actually, maybe I should pick a red or something. Let's just go, yeah. So this line gets ignored here. So I'll just put maybe not used here, and this one here, let's do that as well, just so we've got that in under. And this one here not used in over estimate. Okay, so we see here that our first length that we need to use for the let's do it here. This first length here, this first coordinate is f of x1, not f of x0, and this time we use f of xn is our final value. Okay, so now we come down here and we should look at these two terms side by side. So this term doesn't exist in the overestimate, like this term here doesn't exist in the underestimate. So these two things, I better get rid of that one because that one does exist. Okay. Now, this leads us to the next part, which this is mainly a proof here. It means that if I was going to calculate how different the overestimate and the lower estimate were, I would take them from each other, and this would be equal to the width of this term here that doesn't exist in the underestimate minus this term here that exists in the lower estimate. And we would get that it equals the width. Now, if you remember up here, we came up with this formula for the width, which was b minus a over n. And then we would have the coordinate of whatever b is put into our function minus whatever a is put into our function. So if we're considering these here, I'll use this graph that I had prepared earlier here. So this form here, we would be having the width, and then we'd have just these two values. And remember, we're calculating the limit. Now, as these values here, we think about this sum we came up with here. Well, if we make an infinite amount of rectangles, so you think about these rectangles here, these are still quite wide. If we made them infinitely small and we had an infinite amount of them, the difference between the area upper and the area lower would equal 0 because of this 1 over n, this would approach 0. Similar to in our other topic, throughout the year, we've talked a little bit about asymptotes. This thing would equal 0, and that means if this equals 0, this whole thing here equals 0. So therefore, we have, as the amount of rectangles becomes infinity, the underestimate will equal the upper estimate. And since we have the area of the underestimate, so all the lower rectangles and upper rectangles, we have that at the moment the underestimate is less than the actual area, which is less than the upper estimate for all the values of n. We end up going, well, if the difference equals 0, then realistically, as n approaches infinity, the area of the lower estimate is going to equal the area, and it's going to equal the area of the upper estimate. Okay, now definition time. All right, so the value A, which is our area, is known as, we call this the definite integral. Now, the definite integral has bounds, so the definite integral of f of x from a to b. So we notice that we have this S-shaped thing here. This is the integral symbol. So the area of these curves here, we have the integral here with a lower bound of a. similar to how we've been doing it in our program if you watched the previous video. And our upper bound of b, f of x is our function, okay, and it's with respect to x. So we're looking at the integral, we're looking at the area with respect to the x-axis. So if f of x is greater than or equal to 0, now we haven't really talked about this, but I'll cover this quickly now. This is just the simplest integral we do sits above the x-axis. But we can still take the integral when it's below the x-axis, we just get a negative number. So if f of x is greater than 0 for all a greater than or equal to x, x is greater than a, less than b, then the integral of between a and b of f of x dx is equal to the shaded area. So it pretty much means we can calculate the shaded area here in this particular area. Now, most of the time the questions we're doing here, we're not fully into integration yet. We're defining it. We're mainly looking at, can we define our function? Can we use this definite integral to set out our problem with a diagram? And then can we use what we've been doing previously with rectangles to calculate those estimates? Now, I'm going to leave that there because that should get us through this section here. We're in 4A.2 in our textbook, so this is a chance for you to jump into those problems, still use the program we're using, but we're defining this now with a function. Remember from the last video as well that we can actually do some of our stuff knowing what we know about geometry as well. All right. One last thing, for some of the questions in the text, you will need to consider changing the values of n because some of the n values will take the program too long to process. All right. Thanks, guys.